Hey, my name is Francisco Morales, and in this presentation, I'm going to talk about the use of single-domain antibodies from camelids, nanobodies, in immunoassay development. Nanobodies have been extensively used in immunoassay development, and one of the main reasons why they are so suitable for this application is that they are composed by a single polypeptide chain. That allows the production of nanobodies in bacterial systems in high yields without batch-to-batch variations, something that is a problem in conventional antibodies. Another advantage is that they are very easy to engineer, and that means that, for example, we can create fusion proteins where we can have the nanobody in frame with reporter molecules like alkaline phosphatase or horseradish peroxidase for immunoassay development. There is also the possibility of in vivo biotinylation, chemical enzymatic coupling. We can increase avidity through multivalent constructs, and everything without losing the possibility of the classical chemical coupling that we have been used for decades with conventional antibodies. All these features make nanobodies ideal for difficult diagnosis. And the disease that we address in this research was the human toxocariasis, a very neglected disease, but highly prevalent all over the world. And the main problem on this disease in terms of diagnosis is spotting active cases. To do that, we need to detect the biomarker of the disease, which is the toxocara excretory-secretory antigen. And the problem is that the levels of these proteins are very, very low in the human being. On top of that, there is a problem of specificity. So we need nanobodies that are very specific to avoid cross-reactivity with other elements that is very frequent, especially in tropical settings. And we also need to address the possibility of transport this assay to the field as a point of care diagnostic system. So the first step in the developing of this assay was the generation of nanobodies. And first, we test a sandwich ELISA using monovalent nanobodies against tests, and we found a limit of detection of 156 nanograms per ml. This limit of detection was further improved using bivalent and bivalent biotinylated nanobodies, reaching a limit of detection of 650 picograms per ml. After that, because this is not enough to diagnose human toxocariasis in human beings, we start to play with different detection systems. And the first one was electrochemiluminescence that showed a limit of detection of 200 picograms per ml. And then we decide to convert this assay into an electrochemical assay using paramagnetic beads instead of plates. So in this system, we found a limit of detection of 30 picograms per ml. That is very important, and that allows the detection of human toxocariasis, active cases of the disease. And recently, we improved the limit of detection through an electrochemical redox cycling system using this time alkaline phosphatase as a readout system. Altogether, that means that compared to the first monovalent sandwich ELISA that we developed, we have improved 15,500 fold the limit of detection of the disease, which is very important and it's very high. We also had a chance to test the amperometric assay in a set of samples from children in rural communities with high eosinophilia, and we have a positivity of 53% with no cross-reactivity with other elements. For these experiments, we had a chance also to use multiplexing devices to simultaneous detection of tests in the amperometric reading. And finally, the take-home message that I would like to give to those who are working with immunoassay development is to use the streptavidin biotin system for increasing limit of detection of your assay. The improvement of the sensitivity is tremendous, and we highly recommend this system in your experiments. Thanks a lot, and don't hesitate to contact me if you have any question. Bye.